We all know Renzo Ricca, and his title is here, so...
Thank you very much, John. It's a pleasure to be here. Thank you very much to the organizers to invite me here and to give me the chance to talk about actually it's a little piece of work I'd done some time ago, but I didn't have much chance to talk about, so I'm very happy to talk about this here. So it's basically has to do with the idea to extract dynamical information from geometric information, and well, of course, the idea is also to apply this to complex structures. As Keith mentioned, the first IATAM symposium on topological fluid mechanics was now already 23 years ago. This is a picture from work of Kida. That was then the state of the art, the evolution of a kind of vortex knot. And now, because we are here after some long time, I have to impress you with something a bit more update on the art of computing. I'm not in that, but I asked a couple of friends to help me, and so up to yesterday we just send emails on off, in particular Fazil Hussein and Petros Kumatsakos at ATH sent me a nice simulation about the Olympic rings. So I'm going to talk a little bit about that at the end of my talk, okay? So, but it's due to their work that they did very late, the very last minute of this conference. So the idea is basically quite simple. I will talk about linear and angular momentum in ideal fluids, and for simplicity I would refer as a starting point to a single structure that may be knotted or not. Mind you, is a geometry kind of information that I'm going to talk about, but topology is enters in the picture. However, I have no time to talk about topological aspects on the geometric aspects I'll refer to. So they are quite subtle and very interesting and very diversified, but I apologize for that. Anyway, so we have, say, a structure, quite simple, a tube centered on an axis chi, and vorticity, again, for simplicity, we assume that is just along the tangent directions constant. And circulation, of course, is conserved. Linear momentum, i.e. the impulse to generate this structure from rest in an unbounded fluid domain, is defined like this, but because the vorticity is just given by the tangent direction, I can extract circulation and I can reduce this the momentum to this form. Now the interesting thing, well, we can do the same with the angular momentum. Of course, this is the definition, and we can reduce that in that form. But if we are in this simplified approach, you will realize immediately that x prime is just the derivative of the vector position x with respect to the arc length s, and therefore here you can read out x across dx, which is an area information. And this is surprising that almost nobody used this idea, since we know the conservation of momenta. So I will exploit this information during my talk. Well, is the area. What kind of area? Well, this is a vector quantity, so it's likely to, we decompose it in components, and the area is the area bounded somehow by the line, by the contour line of the projection of a curve in space of chi to the plane along the direction of the components of the vector. So the idea is now, okay, I have a space curve, I project it on a plane, and presumably I can relate the area that I read out from that planar projection to the component of the vector quantity that I'm going to refer to. So I take the projection, a standard projection, a projection that we learn from school, i.e. a projection that produce a nodal curve, a graph, a curve with intersection points. So for each component I will have a graph, and the graph is somehow bounding an area. I said somehow because the graph will inherit the orientation from vorticity, but because it's a graph, not necessarily the arcs will carry the orientation congruently. So we just simply go to the fact that linear and angular momenta are related to these particular areas. I'll focus on these areas because these are not the standard areas. So let me make an example. For simplicity, let's take our preferred knot, i.e. the unknot, and I project it. I get on a plane this graph. This graph will have evidently the region R0, R1, R2, R3, and we have to evaluate, as I said, a kind of area associated with these regions. Pay attention, for example, to the region R1. You see there is an orientation along this arc and the orientation along the other arc, and there is no circulation there. So I have to evaluate the area of that particular type of region. But once I do this, I have this information, the total, say, let me call it signed area, and then I can relate the total signed area to the component of the vector quantity I'm interested in. Well, if we refer to the momentum, then there is, well, in the 19th century, they call it the moment of the area. So there is a distance with respect to which we consider rotation. Well, I must confess that I tried to contact some graph theory people, but I couldn't find the information I wanted, so I wrote what I knew and what I worked out myself. But knowing a little bit of history of science, I've been cautious to give names to things. So I'm sure I gave this talk a number of times now, but not to departments. So suppose you have a component, so the curve is extremely simple. You project it, you have this area, you have this region, and the area is the region, is the information you get from the bounding curve. Now you take any point in this region and you construct the radial vector, a vector that is pointing somehow out in the exterior of this region. Now you consider the black dot. The black dot is the crossing site of this radial vector with respect to the bounding curve of that region. You introduce an index. This index is an epsilon at this point, and this epsilon is an algebraic sign, +1, -1, based on the fact that you construct the rho t, t being the tangent, the rho t, if the rho t is positive, right-handed frame, then you associate a +1 to this intersection point. But maybe you cross a number of arcs, and so you add up this information to this index. I call it Cauchy index. I told you, just to be on the safe side. I don't know, I think it makes sense, but I cannot justify it. The name has some meaning for me, that's all. The signed area. Well, the signed area is just the area, the standard area, the measure of that region, times this Cauchy index. Okay? And so we can work out these areas, and basically my talk is done. I want to show you now how to implement this information gradually, like school. So we start with a simple case, and then I'll show you some possible applications. So we take, in this sense, in the sense of projections, topology doesn't matter at all, because I took a knot, but once it's projected, can be not at all knotted. Okay, but I took a knot. Now consider that I'm lucky that this projection is just the projection of the knot type. And then I do this business. Okay, so I go, each region I count the crossings. So here, this region will have just one crossing, and is +1. And this region is -1, because you see the orientation that I inherit from vorticity, let's say. So the physical orientation goes oppositely in respect to my reference frame, and so I'll have a -1 here. But what about this region? This region here, you see, you take any point, you will cross, for instance, these two arcs, and I count if this is negative, like this one is a -1, and this is negative again, is another -1. And the Cauchy index, as I defined it, is the sum of these contributions. So in this case, will be -2. What about this case, the central region here? You do the same. You take any point. You can go even cross these regions, these 4 arcs. But it doesn't matter. You can choose, for instance, these 2 arcs. It goes like this. So you would have a +1, and it goes like this. So you have a -1. So the total index is 0. But being 0 means that in terms of the momentum, or at least the component of the momentum along the direction of projection, it means that this sub-area, well, at least won't move from the rest, okay, from rest. Equally, you may say that these 2 regions, suppose that the motion is, let's say, forward in the positive direction from the screen, so it means that this motion would be kicked off in the backward direction, compared to this little one region that will be even pushed farther down in the screen. What about projecting structures like these? Well, these are not so strange structures. Can be just a filament that is coiling up in space. And suppose, just for the sake of illustration, that these projections correspond exactly to what you see. So suppose that the areas of each lobe is overwhelmingly higher or larger than the area in the interior region, the dark gray region. Now you count your indices, and you can end up with indices that are prevailingly negative, corresponding to this one. It would mean that a momentum given associated to a structure like that would provide motion in the backward direction, a backward motion. Well, amazingly, I just became to know a result by Barenghi et al. On application of Biot-Savart superfluid vortices, where they found indeed configuration that correspond more or less to, of course this is a sketch, to this kind of diagram, that go backward in space, and appropriately call these structures Crab vortices. Well, can we say something about, well, this is a conjectured, this is a thought experiment that I decided, well, it basically born here when I ran the program Geometry and Topology of Fluid Flows in the year 2000. I then put it in a little paper I wrote. So this is just a thought experiment. You just shoot 2 rings, 2 vortex rings coaxially, choosing the geometry appropriately so that they might reconnect on specific sites that you like, and that can be gauged quite appropriately by using local induction approximation information on local curvature, etc., maybe in an experiment or in numerical simulations indeed. And you would hope by this idea to realize a trefoil knot. Well, if you apply these criterion, this method to this trefoil knot, you would learn that the exterior areas would move with a certain speed, but certainly the greatest kickoff will be received by the central area. Now, I'm happy to report, I'm just back from California, and I attended a very interesting program, and one of the results was the production of a trefoil vortex filament in water. I cannot show you the movie. I saw it. It's very interesting. It wasn't, the people tried very hard to do this way. They did it in another way. There is a kind of embargo posed on the publication of the result. so I'm happy to stay with that, but I'd like to advertise that is the work of William Irvine and his group at the James Franck Institute in Chicago. All right, but I want to say that I immediately asked him, actually we were in touch before my talk and during their work, and they indeed measured these quantities. So it's interesting agreement. Now the idea is that this method is applicable to any complex structure. So let me, of course, if we think of a link or a tangle of filaments, they might have different circulations. We may average out these differences, and we end up with the same information. There is just a kind of average circulation there waiting for the differences. What about links? Just for fun, we consider this projection. Again, it can be linked, it cannot be linked, it can just be one ring after the other, remember, but they are co-oriented, so we expect a sum up of the contributions. We do the same technique, and indeed the central regions we see that it receives the largest kickoff compared to the area. What about this different orientation, opposite orientation? What happens in this case? This can be a colliding head-on collision of vortex rings. Well, if it is a head-on collision of vortex rings, the total linear momentum is zero. And in ideal evolution, it should stay zero throughout the mechanism of collision. And indeed, here we have a zero from the central area, and this plus minus that appear. That is quite interesting, so I will consider again this case. So we have a head-on collision of vortex ring, and then if they are really colliding upon reconnection, we can definitely extract this information. That will mean that if reconnections take place, there is a likelihood to produce small vortex rings as a byproduct of opposite direction. The purpose of my talk is to show you also that this was done experimentally by Lim and Nichols back '92. You can download the movie from Lim's website. There are two different colored vortex rings produced in water. A membrane, kind of membrane is formed. Everywhere is water, and at a certain point a diamond of little rings are formed. And if you inspect clearly, if you inspect let me say the fluid surface that stays at the plane of reconnection, you can easily see this wavy pattern. And if you look at the movie, which I'd like to show you, although is not so easy to see it, but let's see. But well, you have to spend a little time in looking carefully. You can I'm sorry, it's not terribly visible, but if you run it several times, you can see that you see highly waved let's say fluid membrane here is present, and induces indeed up to, I also contact the authors, the slight opposite directions of these smaller rings. And the Olympic rings, same strategy, you do the same. They are all oriented in the same direction. You expect for some reason that they interact, and you expect that there is a shoot-off of these smaller rings. So I'm going just to advertise this improved vortex method by, in particular, by Petros Komoutsakos at ETH. I show you just the frames, and then the movie, and I'm done. Oops. Okay. So this is just their work. I received these files basically 2 days ago. Okay. So these are the 4 vortex rings produced, but I'd like, just finishing, to show you the top view, because without colors this time, because I think is also quite it tells you, it clearly shows you how quickly they are kicked off. So I'm just happy to conclude my talk advertising. They've been so kind, so I'd be happy to advertise their work and their method. Thank you very much for your attention.
Yoshi.
So Renzo, I think counting index is very interesting idea, but I wonder the number, the sign gives you an information, but the number, does it give any qualitative or quantitative information?
Well, yes, of course, because this is an interesting point, by the way. Suppose you have a little area,
Yeah.
and with whatever index you have, say a negative index,
Yeah.
and nearby you have a large area with a positive index. Wait. Of course, you have immediately a quantitative information that probably the large area is prevailing no matter what. However, because it's an area, it's not topology, you can you can extract a little area in the positive direction that compare with a little area in the negative direction. These two sides near the crossings, they would count equally. So you can do a lot of say speculations on these.
You're taking projection, so
Yeah.
projection changes the
Sure.
area.
Sure.
So it gives it somehow loses the information.
No. It gives you the information for the vector quantity you're caring about in the direction of the projection you choose.
He has to take all three.
Oh
You
yeah,
get all
yeah,
three,
three,
and then-
yes.
Yeah, three.
If we have three, yes.
Yeah. Sorry.
Yeah.
But he's just computing the computer.
Okay, well, I think it's time to move on. So let's thank our speaker once more.